Titanium is not used everywhere in an aircraft, but where it is used, it plays a critical role. It sits between aluminum and steel in terms of density and strength, and is chosen when both high performance and durability are required. Engineers select titanium for areas that experience high loads, high temperatures, or aggressive environments. Rather than being a general structural material, titanium acts as a problem-solver material for demanding locations where other metals would either fail or add too much weight. Titanium is valued because it maintains high strength while remaining much lighter than steel. Unlike aluminum, it retains its mechanical properties at elevated temperatures, making it suitable for areas close to engines. Titanium also forms a stable oxide layer on its surface, which gives it excellent resistance to corrosion in moist and chemically aggressive environments. This combination of strength, temperature capability, and corrosion resistance makes titanium ideal for long-life aircraft structures. In civil and military aircraft, titanium is commonly found in engine mounts, pylons, wing-to-body fittings, and areas that carry concentrated loads. It is also used in bleed air systems, firewalls, and selected fasteners where high tensile strength is required. In extreme cases, such as very high-speed aircraft, titanium has even been used for large portions of the airframe to withstand aerodynamic heating. These applications highlight titanium's role in critical, high-demand zones. Despite its high density, steel remains essential in aircraft design. It offers unmatched strength, toughness, and resistance to wear and impact. Components such as landing gear, axles, shafts, and very large fasteners rely on steel because they must survive extreme loads, repeated impacts, and surface contact stresses. In these cases, reducing weight is less important than ensuring absolute reliability and damage resistance, which steel provides consistently. Material selection in aircraft structures is always a balance between strength and weight. Aluminum is lightweight and economical, but limited in temperature and ultimate strength. Steel provides very high strength and toughness, but adds significant mass. Titanium occupies the middle ground, offering much of steel's strength at a lower weight while outperforming aluminum in high-temperature environments. Designers choose among these materials based on where the structure sits in this trade-off space. Titanium delivers performance benefits, but it also introduces challenges. It is expensive to extract and process, difficult to machine, and sensitive to contamination during manufacturing and welding. Maintenance teams must monitor for issues such as fretting, hydrogen absorption, and surface damage. Steel, while cheaper and easier to process, adds weight and may require corrosion protection. These factors mean that high-performance materials are used selectively rather than universally. Modern aircraft are designed as optimized material systems rather than single material structures. Aluminum is used for large, lightly loaded areas. Composites reduce weight and improve fatigue and corrosion resistance. Titanium handles high load and high temperature regions, and steel protects the most heavily stressed components. By combining materials, engineers ensure that each part of the aircraft performs efficiently, safely, and economically throughout its service life.